Welcome to video 58 in the lecture Advanced Mathematic Modeling. So in the last video we looked at metabolic scaling. So we looked how the metabolic rate, so the energy produced by an organism, or in this diagram of a mammal, increases with its body size. And we saw the metabolic rate B increases with the body size to an exponent 3/4, which we called, which is the Kleiber's law. And then we saw that such a power law does not hold only for the metabolic rate, but for many physiological processes like size of organs like the aorta, for the life expectancy, for the frequency of heartbeats, the genome size, and so on. But always not with the same critical exponent, but always with a critical exponent which is a multiple of 1/4. And the question is, what could be the reason for this? And in this video I want to discuss some theories which might explain this. And this is called metabolic theory. So first let's see what would be the most naive theory. In order to approach this a bit more systematically or step by step. So let's say if you would have let's assume we have a machine or an engine. And then you could say that the metabolic rate B should be proportional to the number of units, or the computer power should be proportional to the number of transistors. And if the animal would be a machine, then the metabolic rate would be proportional to the number of cells. Number of cells. And the number of cells would be proportional to the body mass. Yeah? So this means the most naive thinking, if every cell would produce the same amount of heat, yeah, because let's say you have an organism, every cell, all cells basically do the same, they work with a certain metabolic rate, they do chemical processes, dissipate heat, and then you would expect that the metabolic rate of the whole organism is proportional to the number of cells. Every cell more or less has the same weight, and then we would expect that the metabolic rate scales as the mass to power 1. Yeah, and that would be the most naive or most basic finding. Yeah? And you would have this, for example, in machines, engines. The more cylinders your car has, the more power it has. Here in engines, machines, computers. But of course this scaling is also there, not so perfect. It doesn't mean that if you have more transistors that your computer is more efficient. That depends, for example, if you have an algorithm which can use all the transistors, but you wouldn't expect such a decay. I mean, because if we would plot this power law not on a double logarithmic scale, we would have here this typical root behavior, so we would have concave curve, yeah? And yeah, so with more body size, I mean, we don't have less than linearly increasing heat. So somehow the heat of a big animal is not proportional to that what could be produced by all the cells. So what would be the next theory that we could come up with? And that would be the theory, the geometric theory. And so we would try to explain everything by surface to volume ratios. And here we would argue that the heat that is produced by metabolism this heat must somehow be taken away from the organism. So it needs this heat has to be taken away. It's to be taken away by cooling. So because like if we have more and more cells and they produce heat and you need cooling, then you know this in the computer, so you need a fan or something to cool your computer. But so what would be the corresponding cooling effect in an organism? And there typically the cooling goes at the surface of the organism. And then we say, okay, so if you produce too much energy, you would overheat, so you have to reduce the heat production for larger organisms. So the metabolic rate then should scale with the surface, and this scales with body mass to power 3/2/3. So now we would have already a power law which is a little bit, so like here we have a critical exponent B equals 2/3 here, which is 0.66, but I mean it's close by, but the real exponent is 0.75, so the real exponent is a bit more. So the reduction by the surface cooling would be too strong, yeah. So and the data is too precise that this could be just a mistake. Even though there are some claims, there are some animals and organisms where we have such a scaling with 2/3, but the general observation is that we have this exponent 3/4. So the simple surface cooling would not be the correct answer. But to explain again, still the argument would be if every cell, like in the naive theory, would just produce the same amount of heat, then the elephant would just die by overheating, by fever. So the elephant needs to reduce his metabolism in order to have a constant temperature. Yeah? So, but the problem with this here is its close exponent is close to measured exponent (0.75), but simply wrong. So we need a different theory. Yeah? And now there's this is still a debate in science, and maybe I should be careful with what I claim here is the answer. I'm not sure if all scientists agreed on the answer, but maybe the most interesting perspective approach, and one which is maybe the most acknowledged answer where most scientists would agree, that's the metabolic theory by West, Brown and Enquist. So three scientists, West, Brown and Enquist, so West, Brown, Enquist theory. And this basically goes to this what we had already here, that we said maybe a fractal geometry could be behind all of this. So we go to fractals, and this again connects this why this all comes in this lecture, because we studied this fractal in some detail. And so we so the theory says that every organism has a fractal supply system. And what would be this fractal supply system? I mean, this could be our blood vessels. So you could have the system of heart, the biggest vessel, the aorta, and smaller blood vessels. And this supply system, so this fractal supply system, is needed in order to produce the energy to every cell in the organism where we want to produce our metabolism. So basically we say, okay, we have here maybe it's a tissue in our organism, and then we have here the big vessel. So here the blood is coming from the heart, and now this needs to branch in smaller vessels, and these smaller vessels have to branch in again smaller vessels, and these smaller vessels again branch in smaller ones. So in order so that every cell, and we have an arbitrary cell here in the tissue, so that this cell can be delivered by a very small capillary cell. So we go all the way down to the capillaries, so the smallest cell, which then is giving the energy to the cell in the body. So basically this means every cell in the body needs in its neighborhood a capillary where it gets the energy, and this capillary by the supply network needs to be connected to the big aorta which comes from the heart. And then all these things have to come together again in a secondary of such a fractal vessel system where all the small capillaries are taken together, back together. So we have here the blood system. But in a similar way we have so that was the blood system. But our lungs, our breathing system, have something similar. So the air is taken in from your mouth, goes in the lung, and then you have also this branching in smaller and smaller vessels where the air is going, and then again in the capillaries you have the exchange of CO2 and oxygen to the blood. So this lung system, respiratory system, is also a fractal network. And you could have this also in technical systems. Let's say you would have the water, the blood system, lungs, but in technical systems you have the water system in a city. And that's maybe also a good way to think about this. Let's say you have your city and you have many small houses. And in every house you have your water pipes. You can open your water. So every house needs to be connected to the water network. Maybe I do this in blue, the water network here. Water flow network. But these things then have to be connected. So for example, if you have your pipe, then this pipe here is a bit bigger because this pipe has to support 2 households. And here we have another big one which has to support 2 households. We have here another big one. Yeah. And maybe these come together. And then here we have a water thing here, which is very, very thick. You need a very thick pipe because, like, how many houses do you have? Here we have 1 house. Here we have 1 house. But this pipe has already 2 houses there. And if we continue, then we have here a water pipe which needs to be thicker because it has to supply 3 houses. Here we have again 1, here we have 2, 1, 2, and here we have a water pipe which needs to support 4 houses. We have a water pipe which needs to support 5 houses, and if I didn't make a mistake here, and then here we have a water pipe which needs to supply 8 houses. So also now, if you want to make a pipe system where you pump water in the city and you need to go to every house, you need also something like a fractal system where you have a big pipe which is then branching in smaller pipes, and then you have to make care in all the geometry that you have enough water in every small household where the water comes. But you need to maintain a constant pressure that in every house you have the same fluid of water when you open the tap. And so that's a very similar problem than in the blood vessels, where also you need to reach to every small cell. And now the interesting thing is, and so, like, I mean, why? Yeah. I mean, you could think, so why do we need a fractal? I mean, on the one hand, I mean, we need a fractal. Fractal is simply needed in order to get this very big surface, this reaction surface. So fractal gives us a big reaction surface. And we have seen this when we looked for the coastline of England. Then when we looked at very small scales, the coastline was very, very big. And in similar way, also the lungs here, if you look at the total area of the lung system here, even though the lung fits in a small part in my body, the total area of a lung is about 1 tennis court. Or the total length of all blood vessels is, in a human, is 100,000 kilometers. Yeah. And I mean, that's crazy. I mean, how can you get 100,000 kilometers of vessels in a human? And that's because it's a fractal. I mean, in the fractal, if you would continue the branching at infinitum, so you would have an infinite length of the blood vessels. But of course, the branching has to stop at the end members, at the capillaries, where you go to the cell size, because smaller you cannot branch. So there is a certain level, certain small scale where the branching has to stop. Yeah? And so you get a finite length of this fractal, but this is huge. And that's, of course, very good, because we want to have this huge surface where reactions take place. And now the idea is, so the metabolic, according to this theory, the metabolic rate is determined by a surface, but not the outer surface of the elephant, like you saw the big elephants that need to have big ears to cool the body. But instead, these authors say the relevant fractal is the inner surface of all vessels in the body where the reactions take place. So basically all reactions in the living organism take place on surfaces, on the membranes, and we need to increase, to maximize this effective area, this effective surface of the fractal. And now you have to see this fractal needs to be really extreme because it needs to be a space-filling fractal. Fractal needs to be space-filling. Why must the fractal be space-filling? Because we cannot afford to have holes in between. If you would have a hole here in the whole system, then this tissue here would die because it doesn't get energy. This means in this branching process we need a branching to every of these holes here in order to come to every possible cell in the system. And so that was a space-filling fractal, and basically it has a fractal dimension which is, if we have here the surface of everything, the surface would have an area of 2, dimension of 2, and the fractal surface would have a fractal dimension of 2 point something. But if this is space filling, we have 2.99999, which effectively is 3. So the surface, then the dimension of the effective surface is 3. And that's, in the end of the day, that's the reason why we get a scaling which is not 2/3, because that would be normal scaling, normal geometry. But since the fractal dimension surface is not 2, but the surface is 3, so actually we have a fractal dimension of 3/4. So this gives us the exponent 3/4. And sometimes they call this the fourth dimension of life. And so basically, so in a nutshell, the whole theory would say, okay, since we have a fractal, the effective surface needs to be of a fractal dimension 3, and then we replace our normal scaling, just surface to volume, of 2 to 3 to a scaling of 3/4, and that would explain this metabolic theory. But we have maybe to be a bit more careful, because I mean that's kind of the underlying idea of the whole thing. But to see if it works out, we have to calculate everything. And this I want to show you in the next video. This calculation is maybe a bit sophisticated, looks technically complicated, but I mean you just have to take this idea and work it out. And we want to do this in the next video and see how with this theory we can really calculate the exponent and really find this exponent 3/4 in a simple model of such a fractal supply network. But this takes a bit longer, so we will do this in the next video. So yes, for the moment, thank you.